Okay, so today we learn a new vector operation. The ones we did already, add, subtract, scalar multiplication, those are called basic. I think I might have said simple, but I couldn't think of the word. They call them basic. This operation called a dot product is not a basic. It's a new thing. It's not like anything you've done before. The dot product, although you're probably going to think of it like multiplication, because when you show a vector, the dot product of two vectors, you use a dot in between like we do sometimes with multiplication. Just with vectors, it doesn't quite mean exactly the same thing. So this is the definition. If you have the two vectors in component form, right, u1, u2, v1, v2, then the dot product is u1 times v1 plus u2 times v2. Not very complicated. It actually does include some multiplication, but it includes some addition too. It's a combination of the two. Right. In the next, we go on from here. We have we go to space. Everything here is in the plane on a flat surface. And then the next lesson we do these same things in 3 dimensions in space. And then we learn one more vector operation, which also kind of looks like multiplication. We actually use the big X to represent it too, but that's called a cross product. So both of them, in some sense, you're going to think, oh yeah, that's like multiplication, but neither one is quite multiplication. So this is a couple examples of dot products, and I just put their whole examples because there's no point making too much out of it. Right? If we're going to do the dot product of 4, 5, and 2, 3, right, then it's 4 times 2 plus 5 times 3. Right? You're multiplying the first plus multiply the second. Pretty simple. And the result is it a vector or is it a scalar? Is 23 a vector or is it a scalar? It's a scalar, right? Scalar is one number. A vector has got components. Remember? The whole point of a vector is you need 2 pieces of information to define the vector, a magnitude and a direction. One number is not that. That's called a scalar. So the result of a dot product is a scalar. That's a little important. So you can follow the math, right? This one is 2 times 1 plus negative 1 times 2, which is 2 minus 2 is 0. 0 times 4 plus 3 times negative 2, 0 minus 6, negative 6. Right? Not too hard, pretty basic. So the properties of dot products are u dot v, that's how you say it, dot, right? U dot v equals v dot u. So the dot product is, what's the name of that property? Order doesn't matter. It's commutative. Dot product of vectors is a commutative property. Right. The zero vector dotted with a vector equals the scalar 0. Right? What product does that kind of look like? The 0 product of multiplication, in a way, right? What does the next one look like? Associative. Do you see any parentheses over here? It's distributive, right? It's u dot v plus w is u dot v plus u dot w. So it's kind of a distributive property. Right. The next one, we're going to find, if you take the dot product of a vector with itself, then you get the square of the magnitude. Well, just remember, how do we do the magnitude? If I take, if v equals v1, v2, then the magnitude of v would be the square root of v1 squared plus v2 squared. Right? If I square both sides, right, then I'm going to get the magnitude of v squared equals v1 squared plus v2 squared, which is v1 times v1 plus v2 times v2. Right? And that is v dot v. And then the last one, if you multiply, again, what kind of a quantity is this c which is on the outside of the parentheses? It's a scalar. It's in the book, right? So in the book, if they want to say it's a vector, it would be bold, and it's not bold. So this is scalar multiplication times a dot product. Right? So we're going to say c times u dot v is, you can move that c in on one or the other, but you can't do it on both. Right? It's not the same thing as saying cu dot cv. It's either cu dot v or it's u dot cv. So those are properties. So here's some operations. They say, you know, use the definition and the properties to do these operations here. So on the first one, u dot v in parentheses times w. Again, what kind of a entity is u dot v? Is it a scalar or is it a vector? The dot product is a scalar, right? So this is scalar multiplication of the vector w. That's what that's going to be. Okay, first let's do the u dot v. Right, u dot v equals negative 1, 3 dotted with 2, 4, 2, negative 4, right, which is negative 2 plus negative 12, which is negative 14. Did I get that right? Negative 2, negative 12, add them up. So now when we do the u dot v times w, that's negative 14 times w, 1, negative 2. Right, that's a scalar multiplication. Negative 14, positive 28. So let's see. This one ended up being a vector. Okay, let's do the next one. Before we move on to the next one, which is on the next slide, is the result of this going to be a scalar or a vector? Okay, well, let's see. The scalar multiplication 2 times v is a vector. And then you're doing a dot product between two vectors, so the result is a scalar. Dot product is a scalar. So when it says use the properties, right, for this one, we can use this fifth property to do this because we actually already did u dot v. Right? We've already done that. So here we've got u dot 2v, right? According to this property, you know, u dot a constant times v is the same thing as that constant times u dot v. We already did the u dot v, so there's no reason to do it again. Right? What is this going to equal? Okay, this should equal 2 times u dot v, right? According to that property. But on the last slide, we did the u dot v. What was it equal to? Negative 14. 2 times negative 14, negative 28. Okay, and the last one is going to be find the magnitude of u. right? We had a property for that. The property was the magnitude squared, right, equals the vector dotted with itself. So let's see, if we're going to do u, the magnitude of u, then let's do u dot u. Edit, undo. Right. U is negative 1, 3. So this is going to be negative 1, 3 dotted with negative 1, 3, which is 1 plus 9, 10. Right. So that tells us that the magnitude of u squared equals 10. Okay. But we don't want the magnitude squared. We want the magnitude. So we will take the square root. Right? Take the square root. So the magnitude of u equals the square root of 10. So these dot products are easy, right? Sorry. Good. Good. Okay, so dot products become useful when we talk about knowing angles between vectors. We have a formula for the angle between vectors, right? The cosine of the angle between two vectors is this. If the two vectors are u and v, and they are non-zero vectors, right? They have some length to them. It's u dot v in the numerator, and the magnitude of u times the magnitude of v in the denominator. That will be the cosine of the angle. And then how will you find the angle? If you've calculated the cosine, how do you find the angle? Take the cosine inverse. Right? So this is going to give us the cosine. Then you're going to have to find the cosine inverse of whatever that is. Right? Theta equals cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. Good. So find the angle between two vectors, right? 4, 3, and 3, 5. So using the formula, right, the cosine of the angle should be u dotted with v divided by the magnitude of u times the magnitude of v. Right, u dot v, I'll do up here, equals 4 times 3 plus 3 times 5, which is 27. Right, the magnitude of u equals, right, the square root of 4 squared plus 3 squared. Which is 5. And the magnitude of v is the square root of 3 squared plus 5 squared. Which is what, 34? So those are the three things we have to plug into our formula, right? Cosine of theta equals 27 divided by 5 times the square root of 34. So do that math. 27 divided by 5 divided by the square root of 34. I'm getting 0.926, 0.9261. So theta equals the cosine inverse of 0.9621. 22.2. Is it good?
You did 27 divided by 4 times square root of
5.
5 times square root of 34.
Uh-huh.
I think that's it.
What would you get?
I got 31.
So you didn't, it's got to be divided by, you have to have that in parentheses, or else do it like that. 5 divided by, divide by 5, divide by root 34. Yeah.
Okay. How did you see where you got cosine?
Yeah.
You got 0.9261.
Yes.
And then at the bottom you got 962.
I flipped it around. That was a mistake. 9261. I mean, in the calculator, I just, used the 0.9261, which is still on the screen. So I didn't enter it in wrong. It should still be 22.2. I just miswrote it. Good? I mean, got to know the formula. Now, we do something, what we do with this formula not more, but maybe equally, besides finding the angle between two vectors, we actually rearrange the formula, right? Solve it for the dot product, right? Before it was u dot v divided by the magnitude of u, magnitude of v. Well, now we've multiplied that up here. So this u dot v now equals magnitude of u times the magnitude of v times the cosine of theta. Okay. How is it that the dot product could ever equal 0? Given two non-zero vectors, is it possible that the magnitude of u or v is 0? No, they're going to have a positive magnitude when you do that. So if the dot product equals 0, which actually one of our first examples it was, then it must be because the cosine of theta has to equal 0. Okay, well, what angle in degrees does the cosine equal 0? Think of a unit circle. Right? Cosine is the x-coordinate. Right? So it's 0 here. 90 degrees. Right? So theta equals 90. So basically, if you take the dot product and you get 0, that means your vectors are at right angles. Okay, that's how this gets used a lot. Check to see whether two vectors are perpendicular to each other. Sorry. Yeah, I'll use that word for now. See whether they meet at 90 degrees. The check is the dot product equals 0? Pretty easy check. Now, we actually have a different word for that when it's vectors. Right? With straight lines, we call that being perpendicular. With vectors, you call it being orthogonal. Orthogonal means they meet at 90 degrees. Right? Oh. So the check will be, is the dot product 0? If it is, that's it. Yes, they are orthogonal. They've changed, this edition of the book has changed this just a little bit. We'll see in the next example. Good. Thomas, you good? Okay. So are these vectors orthogonal? Okay, so what is the check I'm going to do? So not setting anything equal to 0. What is the check? I'm going to do the dot product, right? U dot V is 2 times 6 plus negative 3 times 4 equals 0. Are they orthogonal? Yes, they're orthogonal. You know, in the last version of the textbook, I don't see that they have this anymore. Is they would say, are they orthogonal or are they parallel or neither? And the parallel, they don't really explain much, but vectors are parallel if they're multiples. If one is just a multiple of the other, that would be the check. So, for example, if I had, 1, 2, and 2, 4, right? Then I would say, are they orthogonal, parallel, or neither? Right? When I did the dot product, 1 times 2 plus 2 times 4, I mean, that's going to be 10. That's not orthogonal. And then you notice that 2 times 1 is 2, and 2 times 2 is 4. So this one is actually 2 times this one is that one. That means they're parallel. I don't see that they have any more problems like that. They've dropped that out of there. But it isn't such a tough concept to understand that if two vectors are, just think, if they're parallel, it means they have the same direction angle. And how do we find the direction angle? We do the theta equals the tan inverse of 2 over 1, or the tan inverse of 4 over 2, right? But in any case, it's going to be the same ratio. So that's how you check to see whether they're parallel to each other. Now, that's all we did, since all we did were the checkpoints from the last section. We're going to go back and do just a few more of the problems that were in the homework exercises that usually cause some confusion. And I think most of the homework that we did from this section, you're not going to be that challenged with it anyways. I did not cover like 2 things that come at the end of that section. One of them being the concept of work, which if you're in physics, you've probably had work as a concept. What is work? Who's got physics? Wake up, Josh. The concept of work means force times distance. So we're dealing with force vectors already, right? And then if you multiply it times the distance, then that is work done. Okay. So we're not going to do that one. In the end, I don't think it adds that much, and it is more like a physics thing. I'm going to show this example here, and then this is going to be one of the ones I assigned from the previous section. Because we've seen this come up before. We saw this come up in one of the trigonometry chapters. But quiet, please. Okay. This one is saying, use the figure to determine the tension in each cable supporting the load, right? So this one is there's 2 cables, and they're supporting this 2,000-foot weight, which is pulling straight down, right? And by the tension in the cables, they mean what is the tension in this cable and what is the tension in this cable. And because the angles are not equal, it's not going to be the same thing. So how many things do you have to solve for? 2. The tension in each cable. We need to know a T1 and we need to know a T2. Okay, well, what do we need in order to solve for 2 unknowns? You need 2 equations. You need a system, right? When you have 2 variables, then you need a system. Understand that this is section 6.3, right? And the next chapter, which we actually already did because we did it in the first semester, is systems. So they're presenting this before they've actually got to the section on systems, the 2 chapters which were systems and then matrices. Because there is a certain level of systems that is just assumed that you've had, that you would be able to solve this with what you already know about systems. So you could see that in both of these, we're looking for the force, the tension, which is a force, that's in each one of these cables, which is balancing the 2,000 pound weight going down. But in both pictures, they're not actually giving you the same information, right? What does this picture have that this picture doesn't have? It doesn't have the angles, right? And we need the angles. So the one I'm going to show you is like one step more complicated than the one you're going to actually do, because this one doesn't have the angles in there already. What it does have are dimensions. So we'll be able to figure out these two angles, right, the A and the B, because we know that this is 24 inches and this is 10, right? So if that's 24, which trig function can I use to find angle A? Right, these two sides are which two sides? Opposite, adjacent, or hypotenuse? Opposite and adjacent, right? So which trig function are we going to use to find the angle? Tangent, right? So this angle A, right? Angle A is going to be the tan inverse of 24 over 10. And you could do that. Second, clear. Second tan inverse, 24 divided by 10. 67.4 degrees. And the angle B will be the tan inverse of what? 24 over 20, right? 24 divided by 20. $50.2. So that's a step you don't have to take on this one because it already has the angles in there. So that should be the easier of the two problems. So now I'm going to go to the next slide, and I've labeled the picture already with the angles in there, right? 67.4, 50.2. And we need to know these two things right there, right? So let's see. Both of these vectors here can be broken down into two components, right? One component is here, and one component is here. And then this has got one component here and one component here. Right, this is pulling up and up. Now, this weight is pulling straight down. Right? It's not moving side to side. So what does that tell you about the balance of this arrow, which is pointing to the left, and this arrow, which is pointing to the right, if it's not moving left or right? They're equal. So one of our equations will set this component equal to this component. And then what do we know about these two components? They're pulling up and exactly balancing 5,000 pounds pulling down. So they add up to 5,000. So there's your two equations with two variables, and you solve the system, right? So let's set that up. Right, T1, let's say, how can we label this better? This one right here is going to be, that's an adjacent side, right? So we're going to use the cosine of 67.4 is this side divided by T1. Right. Well, let's see. I don't need that. Yeah, that is what you got to do, don't you? Let's try this out. Cosine of 67.4 equals that. Let me call that V1. V1 divided by T1. So the V1, that component itself is actually T1 times the cosine of 67.4. That's what goes up here. Okay, what is this one going to be? The V2 then, that is balancing it. This will be the V2. Right, that's going to be the cosine of 50.2 equals V2 over T2, so it should be T2 times the cosine of 50.2. Okay, now, we need to add these two up. What are, this one is going to be the sine, because it's opposite, the sine of, I probably should have labeled these different, but this one here is going to end up being T1 sine 67.4. Right, that's this component right here, because sine of 67.4 equals this divided by this. And then if we add T2 times the sine of 50.2, that's 5,000. Now, if you think that looks complicated, you could always just calculate what's the cosine and the sine of all those angles. Turn them into decimals, right? And then you can deal with numbers instead of sines and cosines. You know, it doesn't matter. How would we normally solve a system like that? What were our methods to solve a system? Well, we had methods and they had names. What was the first method that we learned? Substitution, elimination, and we did one other thing in this class. Well, we used matrices, right? You could always use matrices, but in order to do it in the simplest way, let's just use substitution. And remember what would be the first step in a substitution method? Solve one of these equations for one of the variables, and then plug it into the other equation. Probably easiest to solve for either the T1 or the T2 in the first equation. So let's solve for the T1, right? This T1 is going to be T2 cosine 50.2 divided by the cosine of 60.4. Right, so that I'm going to put all that in a parenthesis. T2 times the cosine of 50.2 divided by the, where is this? Cosine of 67.4. Right, and all of that is times sine of 67.4 plus T2 sine of 50.2 equals 5,000. Okay, now we have one equation and one variable. And let's just turn all this into numbers. I'm going to go ahead and I'm going to calculate all this here as a decimal. Okay. Cosine of 50.2 times the sine of 67.4 divided by the cosine of 67.4. 1.5378. So this is 1.5378 T2 plus the sine of 50.2. 0.7683. 0.7683 T2 equals 5,000. Okay, add these up. Coefficients, right? 1.5378 plus 0.7683. 2.3061. So we have 2.3061 T2 equals 5,000. So divide. T2 equals 5,000 divided by that. 2168.2. Okay, how are we going to find the T1 now that we know T2? Yeah, you're going to go up to, this first equation and plug in for the T2 and solve. It's actually this whole thing right here was the T1. So 2168 times cosine 50.2 divided by the cosine 67.4. 3611. 0.4. So those are the tensions in the two cables. So the main thing is when you see the problem, you've got to be thinking, it's a system. I need two equations, right? It's already got for you, the angles are already there. You don't have to take that step. You just need to be able to break down each one of these vectors into their components. And just like this one, right, this is going to be a sine, this is going to be a cosine. Right? This one is going to still be that the vector that's pulling to the left here has got to balance this vector pulling to the right. And these two components have to add up to 2,000. So there's your system. Honestly, when I do these problems, I prefer to do matrices for them. Just get this onto the other side. And then remember, you set up your matrix. It would be like this. T1, T2 equals, the right-hand side would be 0 for this one, 5,000 for this one. And you can put in your cosine of 67.4, negative cosine of 50.2, and just do it with an a to the minus 1b, and it does the whole thing. A lot less work to do. Now, that's one thing, though. By the time we got to, we're in chapter 6 here, we would not have known about using matrices to solve something like this, right? Because that actually came in not the next chapter, but the second chapter after that. Okay. Now, if you look at this kind of a picture, right, this one is saying this barge is, I think in the problem, it's 6,000 pounds going this way, and there's two tugboats that are pulling it, right? And the tugboats are going in that direction. Now, notice the picture that they've drawn there, that in both of those, the cable, it looks like the tugboats, this is equal, these are equal, the angles are equal. You don't need a system to do that. I mean, they're obviously both pulling 3,000 pounds. So you don't have to solve a system. All you're going to do is say, okay, well, this component of the vector has got to be 3,000 pounds. So just solve for that. It's a fairly simple trig problem. It's not a systems thing because the angles are equal. When the angles weren't equal, then we needed a system to do it. But this one would have the same. Each one would be pulling exactly the same, at the same angle. So let's see. We found the dot product. We know how to find the angle between vectors, and we know how to determine whether they're orthogonal. Plus, there's some added problems which are going back and doing from the homework we did last night. And you got more than a half hour. So even though it's a lot of problems, you can get them done.